Welcome to everyone to this edition of the KISS WASP seminar series. Today we have the pleasure of having Professor Biao Lian from Princeton University, who will tell us about his work on generalizing entanglement entropy to time-like slices in the case of fermionic systems. So, Biao, to you.
Okay, yeah, great. Thank you. Thank you for inviting me to this nice seminar series. And yeah, it's a great pleasure to have opportunity to communicate with this slightly different field of people. I'm a kinetic matter theorist, so yeah, hopefully, yeah. So if you have any questions, please just interrupt me because yeah, maybe there's some terminologies I need to explain more. Yeah, but anyway, this topic I studied here is time direction, entanglement entropy of free fermions. Yeah, this is actually an interesting kind of a side project for me, where we start to explore this concept of entanglement entropy in the sense of space-time. Yeah, so this work will mostly be based on our paper. This paper published 2 years ago, and also there's some results in this new paper to be posted recently. Okay, so let me start. Yeah, let me start with the outline. Yeah, so yeah, first I will briefly review the concept of entanglement entropy, which I hope is already particularly familiar with most of you. Yeah, maybe I'll particularly comment on several examples of applications of the entanglement entropy in traditional physics topics. So then I will show that actually it's possible to generalize this concept of entanglement entropy to space-time, generic space-time slices, but so far only for free fermions yet. So yet we are interested in, of course, generalizing this into interacting systems, but it's there are difficulties in both concepts and also numerical computations. But anyway, so free fermion, even for free fermion systems, I will show it's already very interesting that we have some new understandings of what this can give us. And particularly in the third part, I will focus on the time direction entanglement entropy, yeah, which has more tuning parameters, and you can see what's new here. And eventually, I will put several remarks based on our results so far. Okay. Yeah, so entanglement entropy, it's probably pretty familiar to all of you. It's basically describing the information of a quantum state in a subsystem of your Hilbert space. So, and the most well-known concept is you divide your system into your Hilbert space into sub-Hilbert space A and B. The Hilbert space could just be like A could be a spatial region A, and B is the rest region. And naturally, for spatial region A, you have a sub-Hilbert space, and you can define the so-called reduced density matrix in this subregion A by tracing out the degree of freedom in B on your total density matrix. And this is basically a density matrix describing all the information in subsystem A. For example, it can tell you all the correlations within subsystem A, like endpoint correlation functions, which eventually tells you all the information. Yeah, so this is an example like using string decomposition. Yeah, you can easily calculate this this reduced density matrix here. Also, there's the concept of a entanglement Hamiltonian, which is basically if you regard rho A as e to the minus h, looks like a Gibson state density matrix, then HA is known as the entanglement Hamiltonian or modular Hamiltonian in high energy physics. So the entanglement entropy is here, the von Neumann entanglement entropy is defined as you just treat rho just like the thermal entropy, but instead you use the reduced dense matrix. So SA is just negative trace rho A log rho A. And it's known that this von Neumann entanglement entropy has several typical behaviors. Basically, like for ground states of a system, depending on whether your system is gapped or gapless. If it's gapped ground state, this entanglement entropy will be proportional to the area of the region you enclosed, so-called area law, or up to a log correction if you're gapless. And for all the for like high energy states, excited high energy states, typically this entanglement entropy can have a volume law proportional to the volume of the region, just like the thermal entropy. And it's actually also useful to look at this entanglement Hamiltonian defined as the on the exponent of rho A. So this in general can tell you more information. Which I'll also briefly mention. So actually, diagonalizing this entanglement Hamiltonian give you a entanglement spectrum, which also tells you more information about this separation A and your physical system. An important example, actually analytically calculable example is this 1+1 dimensional conformal field theory, which is known as the gapless theory. And it has a central charge characterizing the number of gapless degree of freedom in the system. In general, this system is interesting because you can calculate entanglement entropy exactly for a subregion of length L, as shown here. In the simplest setup, I just assume the entire system is infinite, and you consider a subsystem of length L. And this entanglement entropy can be calculated using a for ground state of the system or Gibbs state of the system can be calculated using a so-called replica trick. This is basically calculating the trace of a reduced dense matrix to the power n, where this n is integer. And this quantity is known to be calculable by some past integral methods in a Riemann like surface. And as a result, this can be used to calculate the von Neumann entanglement entropy as well by taking this n goes to one limit, basically by analytical continuation. And in this way, Calabrese-Cardy obtain a famous formula for von Neumann entanglement entropy in CFT, which is the C over 3 log L over epsilon. And so importantly, like this is a gapless system, so the entanglement entropy scales as log L in 1+1 dimension. And this coefficient C can be used to extract the central charge or the number, basically characterizing the degree of freedom of the CFT. Okay, so entanglement entropy is also useful in studying the so-called topological ordered states. Here again, I just as an introduction, I'll just briefly mention. So basically for gapped ground states, as we mentioned earlier, the entanglement entropy in general follows the area law. Specifically in 2 dimension, this entanglement entropy will be proportional to the length of the circumference of the subregion. And it was first studied by Kitaf Preskill and also Levin Wen in 2006 that this entropy actually also have a high order correction, which is a constant term to the area law in general for a subregion. And this quantity actually is related to, this is called a topological entanglement entropy, which is related to the number of total quantum dimensions of the anyons of the system. If you're not familiar with this, that's totally fine. So, this is just talking about the use of this entanglement entropy. And basically by doing such a combination of several subregions, you can actually eliminate all the area law contributions and get this number that proves to be useful in detecting topological order. And also entanglement entropy has, beyond entanglement entropy, you can further look at the entanglement spectrum of the ground state. Basically, this is diagonalizing the entanglement Hamiltonian. And in general, for topological phases with edge states, the entanglement spectrum actually also shows these topological edge states, which help you to identify what edge states this topological state can protect. Yeah, so basically, these has been proved very useful in various numerical methods like the DMRG used for calculating one-dimensional states. Okay, so yeah, in general, entanglement entropy is pretty still pretty difficult to calculate because your Hilbert space is exponentially large. But there are special cases like for the Fock states or Gaussian states of either fermions or bosons, actually. So in this talk, I will only focus on fermions for simplicity. But basically, if you have a Fock state or Gaussian states, it was shown like in this paper by Purcell that you can calculate the entanglement entropy in a much easier way. And the trick is basically for Fock states or Gaussian states. For example, such states will be the eigenstates or let's say ground states or Gibbs state of a free fermion Hamiltonian. In this case, you have a weak theorem that all the correlations in your system is a function of 2-point functions, 2-point correlations. So with the help of Wick theorem, it was shown that you can calculate the entanglement entropy in a much easier way. So here, here in general, the free fermion models will have a quadratic Hamiltonian as shown here. And in general, let's say if you diagonalize the Hamiltonian, then your ground state or any eigenstate will be of this form, where each fermion mode has a definite number of fermions here. So that's the definition of Fock state. So in general, as I mentioned, the Wick theorem ensures that all the endpoint functions can be expressed in terms of 2-point functions. So in this case, this of course also holds for your reduced density matrix. Basically, if I'm only focusing on the correlation functions within subsystem A, it has to satisfy this Wick theorem that any endpoint function in the subregion A can be calculated using the reduced density matrix only, and they should be expressible as all contractions of these endpoint functions by Wick theorem. And by this requirement, you can prove that this entanglement Hamiltonian, basically rho A, defined in this form, this HEA has to take a bilinear fermion bilinear form as shown here, up to a constant. So in this sense, your reduced density matrix is required to be take a form like a Gibbs state of some free fermion Hamiltonian, effective free fermion Hamiltonian. Okay, so moreover, this entanglement Hamiltonian on the exponent can be calculated derived from the 2-point functions in your system. So if you calculate all the 2-point functions, so here the Ci and Cj dagger satisfy the canonical commutation relation. They are just the Euro-fermion basis of each site. So in general, you can calculate the 2-point function Cij defined in this way, just within the subregion A. This defines a matrix Cij within system A, where the size of the matrix is the number of sites of subsystem A. And you can show that this matrix kappa ij in your entanglement Hamiltonian is related to this matrix, correlation matrix C, in this way. Kappa ij is just given by this formula. So once you calculate this Cij, you already know your entanglement Hamiltonian and thus your reduced density matrix. And this further allows you to calculate the entanglement entropy. So one thing to note that is, so if I assume this matrix Cij have eigenvalues this Cij, then this eigenvalue is always between 0 and 1. And this is because your number occupation of the fermions is between 0 and 1. So this entanglement entropy is then given by this formula. In terms of the correlation matrix C, it can be written in this way, or in terms of the eigenvalues in this way. Yeah, if you're familiar with the thermal entropy expression, then replacing these eigenvalues by the energy eigenvalues of the fermions give you the thermal entropy. So basically, they follow a similar formula here. Okay. Yeah, so that's basically what we know about the calculable examples in entanglement entropy previously. So now we ask the question, yeah, so can we generalize the entanglement entropy for in general in space-time or a time direction interval? So like earlier in the CFT example I talked about, we're calculating an entanglement entropy of a spatial interval. So does it make sense to consider a time direction interval? So yeah, previous to before our work, there are a few previous ideas which actually are different from our idea that try to generalize the entanglement entropy to time directions. Yeah, but they all have limitations and actually physically, the physical interpretation is quite tricky. So for example, in the context of a conformal field theory, it was studied in these works that, for example, yeah, and so the naive idea is you can analytically continue your CFT formula and the Calabrese-Cardy formula by a weak rotation of a spatial length L into a time direction T. Yeah, the weak rotation introduces a imaginary part I, of course. So then your the typical Calabrese-Cardy formula will become this formula where you get an imaginary part from this weak rotation. So yeah, so this is of course problematic because you get a complex number now. And so in these works, they show that this can be understood as a pseudo entropy, which does not need to be a real number. And actually, they have a way to understand this entropy as an entanglement entropy, pseudo entanglement entropy of some non-Hermitian quantum systems. Yeah, of course, that's not what we want. We still want to talk about the Hermitian quantum systems. So the other idea is known as the temporal entanglement. Yeah, this is mostly studied by Dmitry Abanin's group. Yeah, basically what they propose is, well, in simple words, you can view this time direction as some kind of a spatial direction, and rewrite your Hamiltonian as your Schrödinger equation as a transfer matrix in the x direction instead of a Hamiltonian evolution in the t direction. So in this way, yeah, basically, if you know that some initial value on a certain site and evolve it in the positive x direction, you can get some effective Hamiltonian, which is the transfer matrix. But this transfer matrix is not a Hermitian Hamiltonian. So instead, it again falls into some non-Hermitian setup, and you can define the eigenstates of this transfer matrix and study the entanglement properties. Yes, this is one way of explaining their idea, which I will not go into more details. But basically, the point is, the entanglement entropy defined in this way is also not a entanglement entropy of the actual quantum state. Yeah, so the question we ask is, can we define a entanglement entropy in a conventional sense that it describes the entanglement entropy of quantum state in a certain sub-Hilbert space? Yeah, so in general, we consider a generic space-time slice as shown in the yellow region here. That's not at the same time. So basically, to define entanglement entropy, you just need to define sub-Hilbert space properly associated with the space-time slice A. So the question becomes whether there is a sensible way of assigning a sub-Hilbert space HA to your to the slice I draw here. So suppose once I define the sub-Hilbert space, then things are easy. You just decompose your Hamiltonian, your Hilbert space, total Hilbert space, as HA times the complement HAC. Then you can define the reduced dense matrix by tracing out the other part and define the entanglement entropy in the Euro way. Yeah. Also, it may be confusing, like if I consider the state at different time, how should I understand the quantum state? Which time should I take? So actually, it's important to take the Heisenberg picture here. So in all my talk here, I will be talking about the Heisenberg picture. In Heisenberg picture, the quantum state alpha is time independent, so you don't worry about which time I'm talking about. Instead, it's the operator that becomes time dependent. Okay, so again, so like for this Eurospatial spatial slice case, HA is pretty simple. It's just the product of the on-site Hilbert space of a different sites. That's what we know from before. So if I have a general space-time slice, actually the important question is because your operator keeps evolving as function of time, you can define like the on-site Hilbert space as the space where your operator acts on at a particular time. Because your operator evolves as function time, actually the on-site Hilbert space at different time are no longer orthonormal to each other. That's why you cannot simply do a tensor product of these on-site Hilbert space to define Hilbert space. So instead, we define the sub-Hilbert space as follows. Of course, for now, it's just a general definition which you cannot use at all. But I will show like for free fermion how do we really get it. But basically, the sub-Hilbert space HA should be the smallest Hilbert space that can give you all the correlations within slice A. So here, all the correlation means if I look at all the operators within the subregion A in the Heisenberg picture, yeah, so basically I should only need the information of this reduced tensor matrix A, then I know all the correlations between all these endpoint, all these operators in the slice A. And yeah, basically we define this HA as the smallest Hilbert space that can do this. Okay, yeah, because that's actually naturally reduces to the spatial case, like this HA is the smallest Hilbert space you need to characterize all the correlations, equal time correlations within the sub-Hilbert space. Okay, so for free fermions, yeah, again, like this definition is pretty difficult to use, especially for interacting systems. But for free fermion systems, it becomes easy to identify the sub-Hilbert space. Again, here we assume your Hamiltonian takes this bilinear form. So the other point is when you generalize the concept into space-time, Hamiltonian does play a role because in Heisenberg picture, all these operators evolve by this Hamiltonian. Okay, so we assume this slice A contains a finite number of points, k points. In general, this well, it might be possible to push it to infinite, but for practical purposes, especially also for lattice models, we only deal with finite things. So we assume there are a finite number of k points, space-time points in the slice. And on each space-time points, for free fermions, here we assume 1 fermion degree per site. Then you only need to know the only operators, linearly independent operators at each space-time point is this fermion creation and annihilation operator evolved by Hamiltonian H. But importantly, because the Hamiltonian is a free fermion Hamiltonian, after the evolution, I can rewrite this operator back to time t equal to 0 in terms of the operator at t equal to 0. Because a fermion operator after a bilinear evolution by a bilinear Hamiltonian is still a fermion operator. When you rewrite it back to t equal to 0, it's still a free fermion operator. It's just a superposition of different fermion degrees. So this makes it actually interesting. Basically, we can look at their anti-commutation relations to tell whether these operators are orthonormal to each other. So these operators, fermion operators at different time, they do not commute to a delta function, but because they are fermion operators, they still commute to some numbers because basically at time t equal to 0, they all commute to numbers. And this matrix is a Hermitian matrix here. Okay, so then our goal is to characterize all the correlations of these fermion operators within the slice. So then it's convenient to find a orthonormal basis for all these fermion operators within subregion A. You can do this by actually, if this matrix B is non-singular, then you can define matrix M is roughly speaking like 1 over square root B. By defining this matrix, I can do a linear combination of all the fermion operators on different space-time points into new basis dm. Then it's easy to prove that this new basis dm will be satisfying this orthonormal commutation relation. So they represent the same amount of degree freedom as these CR and TN, because it's just linear recombination, but now you find an orthonormal basis for them. So then actually it's pretty straightforward that your minimal sub-Hilbert space in the subregion A is just spanned by the Hilbert space of all these dm dn operators. If I have k spacetime points in the spacetime slice, then this HA is a 2 to the k dimensional Hilbert space. Basically, this is the basis for this Hilbert space. Basically, they are spanned by these fermion operators dm dagger. So these dm and dm dagger operators, they are not necessarily local in space-time in space, because you just found them by some linear transformation, which is not necessarily local. But basically this depends on the Hamiltonian you have in your system. So this Hilbert space does encode the information of the Hamiltonian. So in general, you don't actually the choice of M can be is not unique, and you can choose any of them, and you can prove that if you want just interested in here calculating entanglement entropy, it doesn't matter which M you take. But in general, there's a more convenient basis you can take. By the QL decomposition, you can take this matrix M to be lower triangular. It has some advantage, but not that important here. But anyway, I do want to comment in this lower triangular form of a matrix M. You can define, for example, if I define a Cauchy surface which completes the entire space-time, if I'm interested in subregion A and its complement AC, I can ask whether I can define fermion basis on this non-constant time slice. And in general, following a similar idea, you can show that in subregion A, of course, first you can define those fermion bases dm. And in AC, you can also define a set of fermion operators dm. So in the spatial case, like the bases of subregion A and AC are independent from each other. But in this case, actually, you can show that basis dm, the orthonormal basis dm in subregion A only depends on the fermion operators CR and Tn in subregion A. That's like usually what we think. But for the complement, the basis has to depend on both the space-time operators within A and AC. Yeah, so basically you cannot find a perfectly orthonormal basis for A and AC. Well, you can find an orthonormal basis dm, but they are not locally locally associated with the space-time slice. Okay, anyway, so with that new basis dm defined within subregion A, the rest of the procedure is pretty straightforward. You just define your 2-point correlation functions now in terms of this orthonormal basis D dagger and D. It's important to use an orthonormal basis because actually in the previous calculation for Gaussian states, there's the implicit assumption that all the fermion operators are orthonormal bases. So basically, if you calculate this 2-point correlation dm, your entanglement entropy will just be straightforwardly given by the previous formula for Gaussian states. You can rewrite this dm matrix dm in terms of the space-time correlation matrix Cm. This is probably like the straightforward 2-point correlation functions you would expect between two space-time points. But basically, you need to transform this C by the matrix M, which transforms you into a orthonormal basis. So that's the difference. So for generic spacetime slice, here I will just only show one example. Actually, yeah, this example is basically I take a straight line segment at angle theta as my spacetime slice with 1 point per site, as shown here. Then I can calculate the entanglement entropy for 1D gapless fermion ground state. This is the simplest example we can calculate. So in this case, even though this is not a relativistic example, in non-relativistic setup, there's also a concept called Lieb-Robinson velocity, which is roughly the maximal velocity information can propagate. This is roughly the maximal Fermi velocity in your system. It plays a role of something like a light cone. If I define this velocity as 1, you can roughly indeed see that when your slice is more space-like, when theta is smaller than pi over 4, it's kind of approaches the spatial result 1/3 log L here because central charge is 1 for this gapless fermion. And when your system becomes time-like, this entanglement entropy becomes a volume law in time, actually in length L. Of course, in this case, length L and time t of the span of this slice is are proportional. Okay, this volume law, yeah. So later I will we will see how to understand this volume law as well. In the pure, basically when in this time-like cases, eventually approaches the time direction entanglement entropy. Okay, now let me proceed to understanding the time direction entanglement entropy specifically. Yeah, actually, the extremal case you can take is just you just consider a time-like slice only on one site. Okay, so it's in some sense a local object. In this case, the number of space-time points you want to put in your system is determined by you. Basically, you can put any number of points here. In general, for time t slice, time t interval in time direction, we still assume you only have a finite number of space-time points. That's for convenience of calculations. But eventually, you can take a continuum time limit by making the separation between 2 points we call tau, which we call tau. You can make this tau extremely small and see what this entanglement entropy behaves. Yeah, basically, for a space-time setup like this, we define it as a time direction entanglement entropy. In this case, yeah, basically, we will show that this time separation, tau, between two neighboring space-time points becomes very important. And once you determine this tau, the number of points k is roughly linear in your in your total time t. Okay, again, we consider the simplest example being the one-dimensional gapless free fermion model with the nearest neighbor hopping. So this is a lattice model known to be gapless. And you can control the filling of your number of fermions in the system so that it's a gapless free fermion system. Again, we always work in the limit where your total system size L is much larger than the number of points K in your system. In this case, this Hamiltonian itself actually have some characteristic energy scale, which is the band energy, the bandwidth of the dispersion of this fermion model. Yeah, I hope everyone kind of knows this tie binding model. So if you diagonalize this Hamiltonian, you get a fermionic dispersion proportional to cosine k. Yeah, so basically your energy dispersion has a bandwidth which is 4 times the hopping strength u here. And you can define time scale, which is 2 pi over E naught. That's like a characteristic time scale of your system. And in this way, you can calculate the anti-commutation matrix B and the correlation matrix C as we defined earlier. I'll come back to these two formulas later, but yeah, this is so far not that important. Basically, if you calculate these matrices, then you can calculate the correlation matrix in the orthonormal basis and therefore calculate the time direction entanglement entropy. So this is the result we obtained. So first, like this figure, in this figure, we are fixing the total time t, the changing the time separation tau, basically, or changing the number of space-time points you have in this interval. Clearly, you see that the entanglement entropy, so each curve corresponds to a different filling fraction of the electrons. But the point is, this entanglement entropy does depend on the number of points you discretize this time interval or the time separation tau. So in more details, now we can talk about different setup. If we fix the time separation tau and change the total time t, we can look at how does the entanglement entropy scale as function t. So what we find is when this tau is greater than tau zero, where tau zero, just recall that it's the time scale set up by the Hamiltonian of your system, where E naught is the bandwidth. When tau is greater than tau zero, you find your entanglement entropy follows a volume law, like proportional to t. This also agrees with the volume law we found earlier for the angle theta space-time slice. And intuitively, the understanding is because in this case, when tau is large, these different time points are far separated from each other, and roughly speaking, they behave like some unentangled subsystems. If you trace out the other sides, somehow, yeah, they look like some mixed states unentangled with each other. So your total entropy will just be proportional to the number of points you have, which give you a volume law. So when tau is equal to tau zero, there is a special point. When tau is equal to tau zero, you find your entanglement entropy is 1/3 log t over some cutoff Tc. So this does agree with the the spatial entanglement entropy case, like your entropy is 1/3 log L, and this actually agrees very well numerically. Yeah, but this is actually only a special point. And more generally, if you take the continuous time limit when tau is much smaller than tau zero, actually, as long as tau is smaller than tau zero, you immediately see this effect. Your entanglement entropy becomes 1/6 log t over Tc. So in some sense, if you view t as the length of your system, this is 1/2 of the spatial analog. Yeah, so the question we then encounter is how do we understand this 1/2 factor, additional 1/2 factor in this entropy? Okay. So yeah, there are two pictures. You can intuitively understand why we get 1/6 log t. So the first picture is actually you can ask what does the sub-Hilbert space of a subregion A look like in this case? In this case, my subregion A is a time direction interval here. And in some sense, any point here, if I trace it back to time t equal to 0, it acquires the same information from the left and the right of your of this time slice. So actually, you can show that this time interval can only access the Hilbert space that's mirror symmetric about this time direction slice. Yeah, basically, yeah, that's like a 1/2 of the Hilbert space you can encounter. Well, you can access around this site. So basically, this roughly speaking, give you only 1/2 of the information you can detect by spatial entanglement entropy. Yeah, but this picture is nice on one hand, but also it doesn't have the ability to explain the difference when you tune this tau. It's a bit difficult to understand why the continuum time, this only holds in the continuum time limit. So the second picture is, at this stage, it sounds a bit heuristic, but basically, in a spatial entanglement entropy case, if I think about a spatial length L, if you look at the momentum space, your ground state actually occupies a Fermi C, in the momentum space with two Fermi points, Kf and minus Kf, in the lattice model. If you look at low energy physics, the two Fermi points give you a right moving fermion and a left moving fermion separately. So each of them actually contribute 1/6 log L, because we know a chiral fermion will contribute 1/6 log L in entanglement entropy. So here is because you have two Fermi points, that's why spatially you get 1/3 log L. But now if I look at time direction, in time direction, instead of momentum space, I should be focusing on how the fermions are occupied in the energy space, because time will correspond to energy. But in energy space, you'll find you only at low energies, you only know that your Fermi energy, your electrons are occupied up to Fermi energy. So there's only one Fermi point, which is the Fermi energy. So in that sense, in energy space, your system behave like a chiral fermion. You only have one Fermi point, EF, and that's why you only get one half of the spatial value with coefficient 1/6. So this picture actually can be made more exact, which is in the paper we are going to post soon. It basically, you can understand this more rigorously by looking at the property of these matrices. I will not be talking about too much details, but here these correlation matrix have a property that, like the matrix element only depends on the time separation of the 2 points you consider, like Tm and Tn, as you can see from their expressions. And so matrices which only depends on the difference between their matrix element indices is known as these Toeplitz matrices. And the property of these Toeplitz matrices are, in some sense, can be understood more analytically. For example, for large Toeplitz matrices, you can define a Fourier transform of this matrix element by basically just doing Fourier transform of the time separation of these two indices, Tm and Tn. And this Fourier transform, roughly speaking, to the lowest order, give you the eigenvalues of these matrices. That's some details, but basically it's just like in tight body models. If you do a Fourier transform, you obtain the eigenvalues of your energies. So in this way, you can calculate these matrices, the Fourier transform of these matrices. And the nice thing about this Fourier transform is that in Fourier space, your correlation matrix in the orthonormal basis is, roughly speaking, just become the product, well, actually C theta divided by B star theta. You can calculate this d theta directly. So in this way, you can roughly calculate the eigenvalues of these d theta matrices. Okay, so in terms of this Toeplitz matrices, there's a conjecture called Fisher-Hartwig conjecture, which in a heuristic way is just saying that the entanglement entropy you want to calculate depends on how many discontinuous jump in this spectrum of d theta. What is this jump in d theta is, roughly speaking, can be understood as the Fermi points we mentioned earlier. So that's why in this picture, it agrees roughly with the Fermi points picture we said earlier. So and you can show that when tau is smaller than tau 0, this d theta roughly is a function that looks like this, which only have a jump at this Fermi energy EF. So that gives you a one third log T. When tau is equal to tau 0, that's actually a special point where at your band edge, you get another jump. You get another jump in this matrix. And actually the two jumps together give you the one third. Eventually, when your tau is much larger than tau 0, you actually don't get any discrete jumps, and eventually you find a volume law entanglement entropy. Okay, so that's about gapless systems. So what happens for band insulators? So basically, we further modify the model a little bit by going to the so-called SSH model. And this model is basically giving your one-dimensional chain alternating hopping amplitudes. It's a smaller hopping amplitude between even and odd sites, and larger hopping amplitude between odd and even sites. This gives you a gap. If your system is at half filling, this gives you a gap to band insulator in the system, or something like a massive Dirac fermion, if you look at the low energy physics. So in this case, there are two different dimensionless parameters that changes the behavior. It's entanglement entropy. One is this tau over tau zero. Again, tau zero is defined as 2 pi over the bandwidth, total bandwidth of your system. The other thing is this tau times the gap delta. So I will not explain the details, but basically you can show that depending on these two parameters, interestingly in this time direction entanglement entropy can show either area law or log law or volume law, depending on these parameters. So just to mention, in the spatial entanglement entropy always shows the area law. Just remember that. So yeah, this figure shows the, roughly speaking, the volume law coefficient in different setups. So basically, you can show like when tau is large, comparable to these 1 over delta or the band gap, you can get these volume law coefficient being non-zero. And that's similar to the also for the gapless case that when tau is greater than tau zero, we do find volume law entanglement entropy. But one thing you can ensure that is that in the continuum time limit, when tau goes to zero, you're always in these regimes where the volume law coefficient goes to zero. In this case, you always get an error law, just like normally what we expect. And this is a typical area law regime, how the entanglement entropy look like as a function of a time t, or the number of points k you have in your time slice. Also, this SSH model is known to have two different phases. One phase is trivial, and the other is topological. We can ask, does the time direction entanglement entropy tell the topology of the system? The answer is there is a quantitative difference, but not necessarily that sharp. But the point is, in this case, you have to look at the two-site time direction entanglement entropy, because in this case, each unit cell contains two sites. And actually, you can show that, you can see that the volume law coefficient of the two systems, of the two phases are different, as shown here. In the topological phase, you have a higher volume law coefficient, while in the trivial phase, you get a lower volume law coefficient. And roughly speaking, the understanding is the topological phase actually, if you look at the wave function, the fermions are kind of entangled more in between different unit cells. So that gives you a higher entanglement entropy. While in the trivial phase, you're more entangled within each unit cell. The error law regimes look similar. Okay, so the other example we take here is the so-called Anderson insulator. So Anderson insulator is a very special system which has actually no band gap, but it's an insulator because all the electrons are localized. So basically, the simplest model for this is the one-dimensional Anderson model, where you have a random on-site potential for each fermions, for each site. So this random on-site potential actually give you a localized electron eigenstates in the system, which means, yeah, their wave function would decay exponentially away from certain center of this wave function. Because the electrons are localized, they cannot conduct electrons, so that's why it's also insulator. But if you look at the energy spectrum, it's usually gapless. So for Anderson insulator, if you look at the spatial entanglement entropy, it's still area law. So we want to look at what happens for time direction entanglement entropy. And interestingly, we find it exacerbates the following behavior. Again, this is for fixed time separation tau. We find the entanglement entropy first it kind of grows as a function of time t as t increases, but beyond certain point, your time direction entanglement entropy start to decay as t increases, and it's also interesting that they follow some power law decay behavior, which we haven't understood understood yet. But the important thing here now is it does decay in the long time limit. So why this is the case? Actually, we argue that this is basically similar to the page curve behavior, like in the black hole entropy understanding. So basically, in this case, although your entire system is infinite, as we mentioned, each electron wave function is actually only localized within a length scale psi. So if you focus on one site, actually, each site only sees the effective system size on the order of psi, and this localization length psi. If you consider a finite system psi, as time t increases, you're kind of accessing more and more Hilbert space within this finite effective system size. So eventually, you're on the other side. When t is large enough, you're kind of already seeing the entire Hilbert space within this length scale psi. So you're on the other side of the page curve. So as a result, your entanglement entropy tends to 0 because your sub-Hilbert space HA is kind of exploring already the entire localized Hilbert space. Yeah, but arguably, roughly speaking, you can view this as a sub-area law that as T increases, your entanglement entropy is not a constant. It's not like a spatial case, your entanglement entropy is a constant, but in time direction, it further decays as a function of T. So we call it a sub-area law. Okay, so yeah, with that, let me with several remarks. So yeah, so basically, as we showed, the time direction entanglement entropy actually give you some more information because it detects the property of the Hamiltonian H itself also. So like in the tau much smaller than tau 0 limit or the continuum time limit, your time direction entanglement entropy kind of approaches a log law for extended gapless fermions. And it follows the area law for gapped like band insulators. But interestingly, for Anderson insulators, although it's also insulator short range correlated, but it actually shows sub-area law because of the page curve argument. So basically, you can argue like this time direction entanglement entropy can already tell you some property of the dynamics of the Hamiltonian, whether it's a band insulator with extended wave functions or becomes an Anderson insulator, which has localized states. Also, we show that actually, in this case, the time separation can change your behavior, time direction, entropy. So more intuitively, you can understand this sub-Hilbert space HA as kind of a the Hilbert space of your causal diamond in the high energy picture. If I'm considering a time direction interval, and this is my speed of light, then in general, I would expect my basically, this is exploring the Hilbert space within the light cone or causal diamond of this time interval. And in non-relativistic cases, you also have a rough speed of light, which is known as the Lieb-Robinson velocity. So you roughly also have this picture. But the important thing is this sub-Hilbert space HA is only upper bounded by this Lieb-Robinson bound. So it's exploring a sub-Hilbert space, like as the picture we said is it explores the mirror symmetric sub-Hilbert space of this Lieb-Robinson bound. Also, actually, as your time t, this time separation tau goes to infinity, as we said, this Hilbert space will have more and more space-time points, but eventually, actually, we shouldn't expect the Hilbert space to increase indefinitely because it's upper bounded by this roughly speaking, this Lieb-Robinson bound. And actually, you can show indeed, if you define this anti-commutation matrix B, and you can show that actually only the non-zero eigenvalues of this matrix B give you the effective degree of freedom in the sub-Hilbert space. So you can drop the zero eigenvalue space of this matrix B, and that roughly eventually saturates to the Hilbert space, the largest Hilbert space you have in this time interval. Talking a little bit more about this causal diamond picture. As we mentioned, because your entanglement entropy we showed is actually 1/2 of the spatial value, you wouldn't expect your time direction Hilbert space to be the entire Hilbert space of the corresponding spatial interval A prime. And that's because kind of you're only exploring the mirror symmetric part of this Hilbert space. But there's a sort of time tube theorem, which says if you now have a finite width time tube along this time, then this time tube would contain all the information of its causal diamond. So here the important thing is this has to be a finite width object instead of just like a infinitely thin time direction line. And you can roughly understand because the tube would be able to sense the like mirror anti-symmetric space of your Hilbert space as well. So one question is, if I make this time direction slice have a finite width, do I get similar result as the time tube theorem that you explore more Hilbert space? And indeed, this is actually an exam result from we calculated for like a 2-side, 3-side, 4-side, 5-side time direction interval. In a continuum time limit, you do see that they eventually approach 1/3 or even higher log t entanglement entropy. That's kind of indicating you're exploring more of the Hilbert space. But it doesn't saturate to 1/3. So as you would expect for the time tube theorem. So there's some quantitative difference that is still to be studied. Okay, so the other interesting thing is like the question is, what does this new basis DM we used for reconstructing the orthonormal basis? What does the physical meaning they have? Actually, they do have some physical meaning as discussed actually by this paper by Xiaoliang Qi's group in 2004. Actually, they are talking about a different setup, but basically they are considering a SYK model, which is 0 plus 1 dimensional model. In the large N limit, they can be viewed as a generalized free fermion as satisfying some weak theorem. In this way, they actually constructed a similar degree of freedom DM and DM dagger from the time direction correlations. And they regard this DM as an effective spatial degree of freedom. So basically, they argue that this DM and DM dagger can be understood as a reconstructed box spacetime, 1 plus 1 dimensional box spacetime. And in this picture, they can show there's some duality between the boundary and the bulk. This DM really plays the role of the basis for a box spacetime. So now the question, so the question is, in general, can we have a similar picture that for any model we consider, like this one-dimensional model, maybe on each side you can reconstruct a basis with this DM dagger degree of freedom. The question is, does it give you maybe a 2 plus 1 dimensional reconstructed box space-time? Okay, I think I'm over time, but let me summarize and stop here. Basically we show this time direction entanglement entropy give you a very interesting new probe of the system, which can tell you information about the Hamiltonians. Of course, the important future question is how does this generalize to interacting systems and quantum circuit systems? One intuition we have is this probably cannot be done exactly, but up to some exponentially small errors, you can define this entanglement entropy for interacting systems. But that's still to be studied. Okay, let me stop here and take questions. Thank you.
Thank you, Biao. Thank you for this very interesting talk and very clear. Let me see. Are there any questions in the chat? Not yet. So I'm going to start myself with a question. So okay, there is something maybe. It was a comment. A great talk by Niceto.
Thank you.
So I wanted to understand precisely. So I was very happy that you, at the end of the talk, you gave this intuition with the past light cone, the causal diamond, because my intuition was that the kind of algebra that you defined should be contained there, and this kind of clarified things. But I missed maybe something essential in the way that you define the basis. So let me just maybe try to express in my own words my question. So what you call this sub-Hilbert space, HA, or kind of a,
Yes.
like in the case of of a space like hypersurface, that's like a tensor factor of the subspace. But in this case, what kind of object is it? Do you complete an algebra, or is it just a subspace of the space of operators that you consider? These operators that you define in the Heisenberg picture, now you can consider their linear span, I suppose. Do you also close under multiplication? Do you consider the full algebra that they generate? Or do you only look at?
Yes, yes. So so very good question. So the way I talk about it may be a bit confusing because I talk about operators. I define a Hilbert space starting from talking about operators. Basically, as you said, the Hilbert space, of course, includes all the product of all these D and D dagger operators. Basically, we define this D and D dagger because we want to identify the Hilbert space. So once you find these operators, we define the Hilbert space as the space that this D and D dagger acts on. That is saying like each D and D dagger, DM and DM dagger, have a two-dimensional Hilbert space as a fermion degree of freedom, right? The two states expanding this Hilbert space is 0, the vacuum, and DM dagger times 0. And if you have K, like K operators, DM, then you can generate like 2 to the K dimensional Hilbert space by applying these D dagger multipolars of D dagger. Actually it's maybe easier if I show the basis again.
Yeah, that would be helpful. Yeah.
Yes, so like this is the basis, Fock basis you generate, where these psi-m can be 0 or 1. So of course, like this means you can of course act like the product of all these DM operators on any states in this Hilbert space, and this will be the sub-Hilbert space you generate. And the point is, because if I only care about the correlations within the subregion A, then all these operators can be rewritten as DM, and these operators DM because they are just related by linear relations. Then all the correlations can be converted into some correlations between DM and DM dagger, and it's sufficient to only know the reduced dense matrix within this basis generated by DM to calculate all correlations between DM.
Is there like a picture that we can have? Something like obviously generalizing the tensor products intuition that we have from the spatial, from the space-like case. Could we speak about the subsystem or the sub-Hilbert space HA as being maybe associated? How does it position itself within the full Hilbert space? Is there some kind of intuition that we can get? Like, is it associated with a subalgebra, or is it a subspace of the Hilbert space, or is it a?
Yes.
Oh.
Very good. Yeah, so it is. Yeah, it is like a so suppose I already have K operators DM. It's just the only unconventional thing is these operator DM, they don't have maybe a spatial correspondence. They don't correspond to certain space-time points. There are some non-local operators in general. But suppose I already have K fermion points. My entire Hilbert space like have L sites. That's defined by L. Well, if you define you can define L as normal fermion operators in the entire Hilbert space. That will characterize the structure of the entire Hilbert space. So what happens here, once you know these K DM operators, you can find the other L minus K DM operators as normal to this space's DM. You can always do that by just doing orthogonalization. Then the rest L minus K DM operators will expand the complement of this Hilbert space. So together they still tensor product into your entire Hilbert space.
Okay.
But these Hilbert space, they don't correspond to a certain space-time region. Yeah, actually, this is one of the the picture I showed here. So actually, you can make it. You can show that you can make it such that your KDM operators they correspond to linear superposition of fermion operators within this space-time slice A. Okay, so that's saying your subpure space A kind of is indeed associated with subregion A. But if you want to ask, now I want to ask, what's the complement of this subpure space? The complement of the subpure space, and the definition is you just find the other L minus K number orthonormal fermion operators. But you find those fermion operators are superpositions in general of the entire fermion operators in A and AC. So yeah, so roughly speaking, the complement of the subpure space A, basically the subpure space AC, does not have a space-time, is not a localized object in space-time. Yeah, it acquires linear superpositions from both A and AC. So that's the unconventional part compared to the spatial case.
Yes,
Um,
you mentioned that, and now that you repeated it, it very much clarifies what I was, yeah, the intuition I was searching. So thanks. That's and what
yeah.
about if you do like you develop this work for fermions and specifically you focus on free fermions? All this
Mhm.
is very challenging, maybe to go beyond, but you're trying. What about bosons? Like,
Uh-huh.
do you think that
Yeah.
same type of construction would make sense and work?
Yes. Again, yeah, very good question. So for bosons, yes, definitely everything still works. Basically, as long as you have weak theorem, um, you can see all these can be generalized to bosons. Um, well, it's just a bit more complicated to do bosons. Actually, it's similar for fermions. For fermions, if I allow fermion pairing terms, um, that will make yeah. Then you better use a Marana basis, Marana basis, which is which can still be done. It's just a bit more complicated algebraically. For bosons, usually I guess for people talk about real bosons. That's more like the Marana analog of in bosons. Yeah, so it's just a bit more complicated algebra, but everything is still bilinear, and you can do everything at quadratic level.
Mhm.
Yeah, but we haven't done the actual calculation to see what bosons would behave under this time direction yet. Partly because bosons will have a infinite Hilbert space, and yeah, in some sense less well controlled.
Yes. I mean, at some point you mentioned when you were discussing the ratio of this time, the choice of these time scales, there was this situation in which you get this bulk like volume dependence. But
Mm-hmm.
if I understood correctly, you said that somehow the density, like the whole space is like almost like a tensor product, like independent density matrices, mixed states. So I was wondering, or maybe I misunderstood that part. It was not that. I think there was another slide where it could have been that one actually,
Okay.
where you
Yeah.
said that essentially you have like just uncorrelated mixed states between
Yeah.
like
Yeah.
when
That's
you're in a certain regime. So I was wondering this density matrix that you calculate, whose entropy you calculate, in that case, is it proper to interpret it as entanglement entropy, or is it
mm. So
just a measure of the mixedness of the state somehow?
mm.
Do we have still a
Ah,
totally pure state?
yes. So maybe yeah. When talk about it, it may be confusing. I'm always considering pure states. So in that sense, it is an entanglement entropy. Um, and you have a properly defined subpure space. So it's a yeah, it's an entanglement entropy of the pure state in the subpure space. But this picture, yeah, um, yeah, this is just an intuitive way to understand why it follows volume law. Um, yeah, so roughly speaking, yeah, so more proper way of saying this maybe is, um, when these time points are far from each other, they're actually more similar to the spatial case. Especially if I don't consider a spatial interval, but instead I consider maybe k points which are far separated from each other in spatially. Then it's well, in some sense you can understand it as a combination of a k disjoint intervals. Yeah, if you have k very k intervals far from each other, then the total entropy will be proportional to the number of intervals you roughly have, because yeah, like here each interval is just a point, like let's say spatially. Two points far away from each other are almost unentangled with each other. But each point, of course, it entangles with the surrounding part. So yeah, so this entanglement entropy is kind of counting the total entanglement entropy of each point with its environment. That's why it's proportional to the number of points you have. Yeah, it's similar in the time direction.
I think that provides a lot of intuition.
Mhm.
You mentioned the page curve, and then there was this ADS-CFT picture. I was curious, like, so what do you think? Like, do you think that this type of work and this exploration of entanglement entropy can provide insights into, say, black hole physics or other questions that are like at the forefront of quantum gravity research?
Mhm.
What is your
Yeah, well, definitely. But yeah, well, definitely in this example, study by Xiaoliang group, they already demonstrated some ADS-CFT dual with a black hole in the bulk. Yeah, I should say I'm not an expert in this direction, so I cannot say something for sure. Yeah, but definitely, so like one thing they mentioned is this 1/3 log t behavior. Sorry, 1/6 log t behavior. They kind of have a similar result. So this 1/6 log t behavior is kind of indicating you only have a chiral fermion in this reconstructed bulk. That's kind of saying, well, as far as I understand, that you only have fermions going into the black hole in some sense. Yeah, so there's some picture you can understand from the black hole picture here. But the other thing is actually this is what I'm thinking about. Maybe interesting is this DM basis, as I mentioned, is not unique, not a unique basis. It depends on how you define your matrix M, and this matrix M you have some degree of freedom to change this matrix M. It's just like a basis transformation between these among different basis DM. So the question is, does this DM correspond to some, what's the physical meaning of these different DMs? So in their work, they talk about like whether you choose this M to be upper triangular or lower triangular, that kind of correspond to the incoming or outgoing light cone coordinates. So yeah, maybe in some sense, this change of basis M correspond to some reparameterization or coordinate redefinition of this bulk geometry. Yeah, there are all kinds of these correspondence where people can study. And especially in this case, if I consider one-dimensional chain, I have one more dimension. Does that really give you some two plus one dimension bulk? Yes, yeah, so far, yeah. I should say I don't know what to predict, but it's certainly a very interesting direction that has been already partly demonstrated in this SYK example.
Yeah, it's really interesting to see how far one can go in extending spatial concepts to the time-like direction by exploiting the Heisenberg picture. In our community, we are exploring alternative, approaches to maybe to discuss quantum physics in space-time, which are a bit more like taking a tensor product in time, which is a bit different than working in the Heisenberg picture, and that provides other types of intuition and maybe ways of thinking about causality, causal structure. But it's really impressive to see how these results and the understanding that you provided in interpreting them. Is there any question from the audience? If not, I will ask one more before closing. I was curious, you mentioned there is something about this cylinder. Francesca, is this a
No, just saying, going ahead with your question.
Okay, I go ahead. So you mentioned this result about putting some kind of volume around the time direction, so this cylinder, and there was so this I didn't fully understand. There was you suggested there was some discrepancy between your results and that formula that other people have obtained. And did I understand correctly? Yes, this you said that your in the continuous limits, your thing doesn't saturate to the same to the same constant as what people. So can you explain how these other methods, how these other results has been obtained? What is the connection?
Yeah, sure. Yeah, I might be a bit fast here. So so first, well, there's no other like similar numerical calculations, but this is what my naive expectation from the time tube theorem. The time tube theorem is saying as long as your time direction interval is a finite width tube, basically that means you care about the operators within this tube. Then, like the correlations within this tube will contain all the information of the entire spatial interval given by this Cauchy diamond. So in that sense, I would expect if I consider a tube and I calculate entanglement entropy for this tube, I should get the same entanglement entropy as the spatial interval A prime, which is 1/3 log L, or translating into T, that should be 1/3 log T. So what we do is then we consider this multi-site time direction interval. That's like saying giving the time slice some width. And we calculate whether it's in the continuum time limit, what's the coefficient in front of log T. This figure is showing the coefficient in front of log T. So what you can see is like for two sites, it does approach approximately close to 1/3. So 1/3 is the expectation from time tube theorem. But time tube theorem first is of course only for relativistic theory. Here we're considering a non-relativistic object. So so it works well for some cases. It's approaching this 1/3, which is the same as spatial case. But like for this 3-side case, it approaches a different value. So we don't know yet what happens here. So basically that's what I mean. So it's not quite clear whether non-relativistic models give you something different compared to time tube theorem.
I see. So the difference was that this was a relativistic theorem.
Yeah, so this was what I expect from the dashed line is what you expect from the time tube theorem. It should be the same as spatial.
Question by Ali, but did you? It was withdrawn. Ali, do you hear me? Maybe he's out. Okay. Well, okay. Well, I don't see then this quote. I think that the question that was raised has been retracted because maybe the person left. Well, then let's thank again Biao Lian for this very interesting talk, and thank you for joining us.
Thank you so much. Yeah, thank you so much for listening.
Thank you. And goodbye, everybody.
Goodbye. Have a nice day.
Yes, same to you.